Good morning, everybody. Cal here with section 5.4, Uniform Continuity. So uniform continuity is a slightly more tricky concept than normal continuity. Um, and I will say your book does not do the world's best job of presenting it. Um, do read what's going on here carefully. And remember that the book is trying to motivate a definition of uniform continuity. It also might be easier to understand what's going on here if you replace the U's in this first blurb with C's. We've been dealing with continuity at a point C in our domain, and your book for no real reason changes the C's to U's in this section, which is confusing. So be aware of that. The idea behind this discussion here, and I'm going to move on to the next page, is that continuity of the function that they're giving in this first motivating example. When you choose the delta in your definition of continuity, this delta depends not only on epsilon, but at the point, C or U, whatever you want to call it, where we're at. Delta is a function, in this case, of epsilon and U, or C. And you've seen this happen in your proofs. We've definitely seen examples where, in order to prove that something is continuous, that a function is continuous at a point C, our choice of delta depends on that C. So the idea is that a function f is uniformly continuous on a domain or on a certain subset of its domain if it's continuous and if the delta depends only on epsilon and not on u. With that in mind, make sure you understand this definition 541 and how it compares with the usual definition of continuity. This is the most important point in this section, is that the only way that these definitions differ, uniform continuity and normal continuity, is what delta is allowed to depend on. Once you understand that, the rest of this section isn't so bad. The book formulates criteria for non-uniform continuity, and make sure you understand that. And then we have a theorem which is pretty cool. It says that if f is a continuous function on a closed bounded interval, then f is uniformly continuous on that closed bounded interval. And the proof is worth reading. Then we get into a discussion of what are called Lipschitz functions, and kind of like contractive sequences were Cauchy, but Cauchy sequences were not necessarily contractive. Lipschitz functions are going to be uniformly continuous, but uniformly continuous functions are not necessarily going to be Lipschitz. The definition is a pretty simple one. There is a k so that f of x minus f of u is always less than or equal to k times x minus u. We've actually done a homework problem that proved continuity from this condition. The first theorem is that if f is Lipschitz, then f is uniformly continuous, which I already mentioned. And if we can page forward here, I said if we can page forward here, hold on. There we go. We have a couple of examples. And then we get into this continuous extension theorem. It's a full characterization of what it means for a function to be uniformly continuous. The idea is going to be that we want to know what happens if a function, what do we need in order for a function to be uniformly continuous on a bounded open interval? And the answer is, if we can extend that function in a continuous way to a bounded closed interval, then it's uniformly continuous. So with that in mind, we have a theorem here which we're going to use in that proof, which is interesting. And then we present and prove the continuous extension theorem, which is what I just stated. A function f is uniformly continuous on the open interval a to b, if and only if it can be defined at the endpoints a and b in a way that the extended function is continuous on the closed bounded interval. So make sure you understand that. We're not going to cover the rest of the section on approximations. So I will say that the results in here are kind of cool, especially the one at the tail end, the Weierstrass approximation theorem. This is an important theorem. But we're not going to worry about it for the rest of this class. So that's all I got for this section.